Good morning and good afternoon. This is Monica Paolini from Senza Fili, and today we're having a conversation on AI, machine learning, neural networks. What is it they do to improve the performance of our networks, to optimize our networks? And I'm talking today to Sachin Katti. He's the CEO of Uhana. Sachin, thanks for being with us today.
Thank you for having me.
So you've been working on Huon now for quite some time. Not too long, but some time. Can you tell us what is the Huon is doing?
Sure, yeah. Uhana is a little bit more than 2 years old now, and what Uhana is doing is it's building a AI-enabled control plane for mobile networks. So it's really trying to apply principles of real-time AI to figure out how to build a control plane and do network optimization, automation, and application acceleration in mobile networks.
That's a great task ahead of you. Now, before we get into the network, let's sort of step back and talk a little bit about AI, machine learning, neural networks. So there's a lot of tools that we have there to improve performance. Can you tell us about what is that you're using and why?
Sure. I mean, I think maybe it might make sense to take a step back, right? So I think what is happening with networks is there's a lot more programmability coming in the networks. So with the advent of SDN and 5G, we are seeing a lot more knobs available inside the network to be able to dynamically tune it for a variety of applications. And the challenge, of course, is that all of these knobs add complexity. They all have dependencies on each other, and it's really hard for humans to figure out how to program them to achieve a particular objective, whether it's network optimization or optimizing an application. So what Uhana is building is really that real-time engine that learns the control plane of the network, right? That really learns how to tune all of these knobs from the data itself, rather than humans trying to tune these things. And kind of the principal technologies we used are things like deep reinforcement learning. So deep reinforcement learning, for example, is a very recent technique that was initially made famous by Google when they used that to beat the best human player in AlphaGo. And if you think about what is happening in that game, the moves you make on the game board are like control knobs, right? And the objective here is to win the game. And the program, or the deep reinforcement learning technique, basically learned what is the right set of optimal moves to make to be able to win that game. And in some sense, the network control problem is similar, where you are trying to figure out what are the right set of control knobs to change to achieve a particular objective. So that's kind of one of the fundamental techniques that we are using to build this control plane.
Absolutely, and you know, as you mentioned, there is an increase in complexity. There are so many knobs, and humans are not capable to deal with all of that. As we used to pretty much do in the past, it was easier, and so we need to have this sort of a continuous learning, and we need in learning in this it's a continuous loop. It's not like you learn and then you pack and go home, right? It's just it's an ongoing process.
Yeah. It is a dynamic system, right? So the network keeps changing underneath you, and it's hard to keep track of all the changes that are happening. New applications keep coming, and the rate at which new applications come is continuously increasing. It's not a set of static applications like in the past where you had just voice and maybe some limited form of data, but nowadays the network is being used for a variety of new applications continuously. So because these things are so dynamic, your system, your control plane also needs to continuously adapt and learn what changes are happening, and then adapt and tune the network so that it can meet the needs. So it's not enough to offline and statically analyze something and then just deploy. You always have to monitor and continuously learn to make sure that you are running the network efficiently.
Right. Now, let's talk a little bit about what is that you need to learn in a network to optimize it, and you work at different levels. So can you walk us through in terms of what is that how is that you're trying to tackle the issue of optimization in the network?
Right. So I think Uhana's control plane actually controls both network layer control knobs as well as application layer control knobs. So it learns how to control both layers, different layers in the stack. So let me start with the network layer first, and then I'll talk about the application layer. So on the network layer, what are you trying to accomplish, right? So you're trying to accomplish what you're trying to learn when how network performance is happening in real time, and that could be at a variety of granularities, at the level of a single subscriber, or it could be at the level of a cell or the entire region. And then not only do you want to monitor it, but you want to proactively identify when problems might be happening. Right? So if you're reacting, by then it's too late, subscriber experience is already hurt. So you want to be able to predict and proactively identify anomalies. And once you have anomalies, you also want to learn how many people is it impacting. Because inevitably a network is going to have a lot of problems, a lot of anomalies. And if you try to chase down every one of them, you just don't have enough people even to chase down and look at all of these issues. So the first task of learning after detecting proactive anomalies is to learn what is the impact each of these problems is having on the network or the users. And then for each of these high impact anomalies, try and classify it into a bunch of root causes. What is a likely explanation for this particular problem? And that's, at this point, this system can act as a human augmentation system. So it's using learning to make humans more productive, right? And then you can still expect the human to take the corrective action based on the root cause recommendation. The last stage here would be once there is enough trust and confidence in the system itself could do closed loop control. So from the root cause classification, the system can then use learning to also learn how to change the configuration or the control knob in the network to automatically fix the problem. And we are already seeing some instances of that, and that will happen more and more over time because you need to optimize more dynamically and in more real time. If there is a human in the loop, there is always inevitably some latency before control is applied. But for future applications, when you need real-time control, inevitably there will be closed-loop control that will happen in this system. So that's on the network side. Right, on the application layer side, similar to networks, you have a variety of knobs to play with in the application layer. So to take an example in video streaming, you can continuously change the bitrate at which video is being downloaded, right? And that is in response to what is happening with network conditions and so on. So similar pipeline where you're taking in data from the network and the application, you're predicting or forecasting what kind of connectivity, and by that I mean throughput and latency, this particular device. So this is now happening at the granularity of a single user. So this particular device will get in the future, and future here is near term, right, in the next 30 seconds or so. And then based on that prediction, you are then learning what control knob to change in the application. So in video's case, what video bitrate should I download the next 4 seconds of video at, so that I optimize the video quality of experience, which could be things like video bitrate, rebuffering, and other such metrics. So the flow is the same. You're monitoring in real time. You're predicting anomalies or connectivity conditions. And then based on that prediction, you're learning what control knob to apply. And that theme, that pipeline applies both to applications and to networks.
Absolutely, and the two work together, but in a very different way. So they address different issues. So let's talk about the applications a little bit more, and then we can go back to the network.
Sure.
So the applications, clearly there is an application provider, there is an operator. And so how do you need to work with both of them, and what is that each need to do in order to make sure you optimize the network?
Yeah, I think yes, eventually you need to work with both the applications as well as the networks. And the way to think about the relationship here is that the network is now providing an API, a predictive connectivity API to applications based on data that only network providers have access to. So their network providers are the only ones who really know what is happening globally in the network with every single user, and therefore can give very precise predictions about what is going to happen to each user's connectivity. And the application provider is coming in and basically saying, how do I take this prediction and use that to make informed decisions or control plane decisions in the application so that I optimize my metric of interest, which could be a higher level metric like video experience or video conferencing experience and gaming experiences, right? And that is going to be very application specific. So the way I characterize this relationship is that this new world, the network providers are becoming more than bitmaps. They're actually now providing real-time APIs to a variety of applications on top. And then applications are working collaboratively with the network to take advantage of these predictions, to optimize their quality of experience, And in return, the network operator can also benefit because the application could make decisions in a manner that actually reduces the stress on the network. So instead of trying to push very high quality video in a place where the network is congested, if such an API existed, then the application could also take corrective action so that the network congestion reduces. So it also helps the operator manage their traffic and network much better.
Absolutely. So this is a win-win for everybody, because from the operator, they can use less resources in the network to transmit their data. Yeah. For the applications, they get a better QoE, better experience on the user, and user obviously is going to be happy. Now, you mentioned real time. What is real time for you? I mean, if you look at real time in the RAN, it's going to be much lower than in other parts of the network. So what counts for you as real time?
Yes, so I think real time here for us is in the order of 100 milliseconds to more. And the reason for that is the system that we are building is completely deployed in the operator's cloud. And it is ingesting data from different points of the network and processing that data to build these models. And the kind of control decisions we are making, especially at the application layer, are longer term control decisions. So what is the video bitrate I should play at for the next 4 seconds? Right, for example, is a control decision that the application is making. So for this, the kind of real-time and time horizons you need is on the order of hundreds of milliseconds rather than very small time scales like 1 millisecond that the RAN deals with. And I would actually argue that at very short time scales like 1 millisecond, the decision is best left in the infrastructure because the time period is too short for you to actually apply learning across a bunch of data. There's not enough time to process all that data, and you're often designing more deterministic algorithms that run inside the infrastructure at those short time scales. So we are trying to avoid conflicts with those lower level control loops and running these relatively longer time scale control loops in the cloud to build these APIs to applications on top.
Absolutely. Now let's go back. I guess it's more network and applications. So you mentioned a few times anomaly detection, and that sounds very cool. But it's a very complicated thing because you don't know an anomaly. An anomaly is just sort of, you don't know what it looks like until you see it, pretty much, right?
Right.
And you don't know, especially in a complex network where you have so many variables, so many parameters, it's very difficult to identify it, especially if you want to predict it, to predict something that is going to be an anomaly. So how do you find out what is the anomaly, and how do you detect it and root cause it?
Yeah, so great question. I think the way to think about, to be more precise about the anomaly detection, the technical term for this is multivariate anomaly detection. And what I really mean by that is anomalies are a function of the granularity at which you're looking at it, right? So you could define anomalies at a whole network-wide level, and you could define anomalies at a single user's perspective, right? So it could be at very different dimensions and very different time scales. So the way we have built the system is we are not making any assumptions about what is the granularity at which you are trying to detect the anomaly. So our system basically learns what is normal behavior along every dimension. What is normal user experience given that particular user's location in the network? What kind of link does he or she have to the network and their mobility? What is normal expected of them? And then we are statistically continuously computing what is the current behavior for that user or that subset of the network, and comparing it to what we have trained our models to predict as normal behavior for that region given the current conditions. So the larger level point is that instead of predefining or humans predefining what is normal, the system is continuously learning along every dimension in time and space what is normal behavior, and then in real time it is computing statistically if what it is seeing right now is statistically significantly different from what it is predicting to be normal behavior. And if it is beyond a particular threshold, then it will say this is likely an anomaly. And that gives us a set of anomalies to work with. It basically prioritizes human attention at that point. And then you are going to the next stage of saying, should I even care about this anomaly? If it's just affecting, let's say, 10 users in a network of 1 million users, maybe I care about it less. But if it's affecting 100,000 users, I care about it a lot more. And if it is a more anomaly that I care about a lot, then I go back and say, okay, what are different root causes, and training models for each of those root cause and trying to estimate a score. How much does this root cause explain this anomaly? So is it a fiber cut somewhere, or is it a misconfigured antenna somewhere, or is it a misconfigured new device? A new iPhone model was introduced and there's some bug in it. So is that the common property here? So all of those are potential root causes that we classify and score. What is the likely explanation for that anomaly that we started?
Absolutely, and but sometimes what you hear is that once you have all this this process going on, for the human in there, the human in the loop or just outside the loop, looking at what's going on, this is perceived as a black box because you don't have the same control. This is not a deterministic model where you say there's like if A then B. It is you look at the complex situations, you come up with the with a recommendation, and you might know you don't understand exactly where it's coming from. So there's a perception of a black box. How can you address that? And does it mean that we need to think in a different way? That is like, you know, our traditional binary, well, deterministic, it's either this or this causes that, it is no longer valid. So we need to think about the way the networks work in a different way.
Yeah, I mean, I think there's several aspects to that question, right? So one is we do definitely need to start thinking about network performance and anomaly detection more statistically, right? So, and what I mean by that is inevitably these systems will produce sometimes predictions that are going to be hard to understand, right? And you have to look at them in a holistic manner to understand statistically, is this performance worse than something else. But coming back to your earlier question, the way we design the system, whenever we give an anomaly or a root cause recommendation, we also collect all the relevant data that was used to make that prediction and present it to the human, right? And the reason we do that is not because we want to repeat the analysis. It's just to give comfort and confidence to the human on what are the inputs that were used to make this decision. And that allows the human to decide whether this is a good recommendation or not. But that also acts as input to the system itself. If the human expert operator who has potentially decades of experience sees that this is wrong, that's feedback to the system. And that feedback actually helps us learn better and make a better recommendation in the next phase. So I'd actually say that this is as we said at the start itself, it's a continuously learning system. We cannot just freeze this. And part of that process is the humans continuously giving feedback to make sure that we evolve and adapt the system to do better and better.
And I guess it's a sort of a meta learning where the humans learn from the black box and the black box learns from the humans, that eventually becomes less of a black box. It becomes more, you got more visibility into the black box as well. Now, another thing though here is that your recommendations are going to be just as good as the input data you have. So if the input data is not reliable, good, or is not the right data, then it doesn't matter how good of a AI and neural net you have in there, you're not going to get the right recommendation. So how can you ensure that you have the right inputs to your solution?
Right. So I think great question, right? So a lot of AI, I mean, and I'd say stepping back, the general comment is a lot of the hard work in using AI in networks is in actually scrubbing the data, sanitizing the data, filtering the data, and processing it to make sure that you give the model the right inputs, right? And that's where a lot of our effort goes in. Even among the data we get, there is a lot of data loss, there's a lot of data noise, and a lot of the time that is spent by our engineers is in using domain knowledge to scrub that data to make sure that we don't learn the wrong things from noisy or missing data. And this, as you've correctly pointed out, is going to always depend, there's a dependency on the quality of the data that's coming from the underlying infrastructure. So there is some initial work that has happened where bodies like 3GPP have specified what data should be exposed, but what's not ever specified is how is that computed? How is a particular KPI computed? What is the quality of that KPI computation? And every vendor has their own interpretation of how to compute that data. So some of that the AI can mask because it can learn over time what are the patterns for different vendors' infrastructure and learn to appropriately use different vendors' data in a different manner. But eventually, I think it's important for our whole industry to get more serious about data quality and really start thinking through how do we specify what is the monitoring and telemetry that we want to embed in every layer of the infrastructure, and what quality do we expect from this so that there is no variation across vendors and AI tools can be effectively applied across multi-vendor networks. And that's a role I think where standard bodies and bodies like ORAN have a big role to play in making sure that that happens.
What about 3GPP? Does it have a role in there too?
Absolutely. I mean, I think 3GPP is where it all starts because that's the one body that's already defining all of these standards and interfaces. And I'd say that specifying beyond just control and messaging interfaces, also interfaces on what data telemetry should be exposed by each element and at what granularity is something 3GPP now needs to start thinking about. So, and I think the larger philosophical shift is infrastructure specification has to have AI as a first principles requirement. Today, AI or any of these learning approaches are an afterthought. You specify the infrastructure and then you figure out how to use AI on top. I think if you from day one think I'm going to use AI to run my network and that's how I should specify my underlying infrastructure, you have to start thinking about, as you said, data quality and what is the data that's being reported. So 3GPP is front and center in this whole conversation.
Absolutely. So let me ask you the final question. When you work with operators, how are they reacting to, I mean, this is something that challenges the way they operate their network, their internal culture. So it's a big change. It's from a qualitative point of view, and there's also a lot of effort. What kind of feedback do you get from them? What is it they see as their major challenge and an opportunity as well?
Yeah, I think it's a bit of both. There's tremendous interest, and we as an industry are at an inflection point because we're going from 4G to 5G, and people are recognizing the complexity that's coming, and they realize that they need help. They need modern approaches to deal with this complexity. So there's tremendous interest to use AI to a variety of to solve their problems. At the same time, as you alluded, there are cultural issues. So there is decades of culture built up on how you run networks today. So even simple things like people's compensation in an operational role are tied to specific KPIs. And expecting then suddenly software to be making decisions that impact these KPIs that affect people's compensation is a big cultural shift. So I think all of these kinds of incentives need to be aligned to make sure that AI can be effectively used. And the approach we are taking is we are not trying to replace the human. I think AI ultimately at this moment is a human augmentation tool. The system is still too complex to really let AI run the whole show. We'll get there at some point, but at this point for network operations and management, it's a human augmentation system where we are really trying to make sure that the limited number of experts that we have are more effective by using AI as a way to prioritize attention and give them all the relevant information that's needed to make quick decisions. So that's, I think, how you start build trust, build confidence before culture changes and before you start trusting more closed loop systems.
Absolutely, and you know, and that's the major issue. It's like humans. There are things that we are not very good at. We are very smart, but not very good. Our short-term memory is like less than 10, like, you know, like 4 to 8 items. A computer, you know, anything in the machine, you can deal with any number of parameters at the same time. We cannot do it. So, you know, we don't need to replace humans to do something that we find boring and we just cannot do. So it just seems like, wow, that's the way to go. Well, Sachin, thanks a lot for sharing the thoughts with us. It was a pleasure talking to you.
Thank you. I had a lot of fun talking to you.
And thank you all for listening in. And you can also read this conversation in a transcript form. Thank you a lot.